Hello guys, this is George Kamiti. Welcome back to our channel. Today we have this problem that we should solve, and it says this: for the bar shown in the figure below, calculate the reaction produced by the lower support on the bar. Find also the stresses in the bars. Young's modulus of elasticity 200 giganewtons per square meter. Now in this case we have two bars, bar LM and bar MN. Both bars are hung on the upper support, and the upper support must produce a reaction R1 to counteract the action force that has been subjected on it by hanging this bar on this upper support. The lower support, on the other hand, is producing a reaction R2, since when this bar finally rests on the lower support, it will produce an action force. So the support must produce an equal and opposite reaction. So both R1 and R2 are upward forces, upward reactions. And that's why when we add the two reactions, they must give you an action force which is 55 kilonewtons. Now in this case, the total force in the bar LM will be, we have a reaction R1. So when you make R1 the subject, we are going to have R1 being equal to 55 minus R2. So that is the total force in the bar LM, and in this case it is a tensile force. It is a tensile force. Since LM we have a tensile load of 55 kilonewtons being subjected on it. On the other hand, in the bar MN, the total force will be R2. The total force will be R2, and it will be a compressive force. Since when this bar extends, it will squeeze the bar MN onto this support, which will result to contraction of the lower bar. And therefore, we are going to have this change in L1, the change in length in the bar LM will be given by load multiplied by the length of the bar divided by area times the Young's modulus of the bar. We have already done so many calculations involved, and we have seen how we come up with this formula. And in this case, this rod P is the reaction R1. So the reaction R1 times the length of the bar LM divided by its cross-sectional area times the Young's modulus of elasticity of steel. So this one will be equal to R1 is 55 kilonewtons. We convert it to newtons. That is 55 multiplied by 1000 minus R2, multiply that by L1. L1, that is the length of the upper portion, the upper bar, 1.2 meters. Divide this by cross-sectional area of the upper bar, that is 110 square millimeters. We need to convert it to square meters. So 110 divided by a million, because 1 square meter is equivalent to a million millimeters. So we are going to have 110 times 10 raised to the power of -6 multiplied by the Young's modulus of elasticity, which is 200 giganewtons. Convert it to newtons per square meter. That is 10 raised to the power of 9. So this is the extension in the upper bar, the bar LM. On the other hand, the contraction in the lower bar, that is MN, will be given by R2 multiplied by its length divided by its cross-sectional area times the Young's modulus of elasticity. And as we had said, the total force in MN is R2, which is a compressive force. So that's going to be R2 times the length of the lower bar, 2.4 meters. 2.4 meters. Divide this by Cross-sectional area of the lower bar, 220 square millimeters. So convert it to convert it to square meters. That is going to be 220 times 10 raised to the power of negative 6 multiplied by the Young's modulus of elasticity, 200 times 10 raised to the power of 9. Now, for this bar MN to finally rest on the lower support, we are going to have this change in length, that is extension of the bar LM minus the contraction of the bar MN will give you 1.2 millimeters. So when this bar extends, it will squeeze this lower bar onto this support. So when you find the difference between the extension on this support minus the contraction on this support, you are going to get this space of 1.2 millimeters. So when we convert this one to meters, we are going to have it as 1.2 divided by 1,000, all times 10 raised to the power of negative 3. Now we have the change, we have the extension of the upper bar, which is all that. We also have the extension, the contraction of the lower bar. So we are going to substitute them here in this formula that we got here. So we are going to have this 55,000 minus R2 times 1.2 meters, divide this by 110 times 10 raised to the power of negative 6 times 200 times 10 raised to the power of 9 minus change in length in the lower portion, or the contraction of the lower portion, which in this case is R2 times 2.4, divide this by 220 times 10 raised to the power of negative 6 times 200 times 10 raised to the power of 9 is equal to this space 1.2 millimeters, which in this case is in meters is 1.2 times 10 raised to the power of negative 3. So what we are going to do next, we are going to multiply everything here by the Young's modulus of elasticity so that we remove it from the denominators. So this is going to lead us to 55,000 minus R2 times 1.2 divided by 110 times 10 raised to the power of negative 6. This one will cancel with what we have multiplied there, minus R2 times 2.4, divide this by 220 times 10 raised to the power of negative 6 is equal to 1.2 times 10 raised to the power of negative 3 times 200 times 10 raised to the power of 9. So we have removed the Young's modulus of elasticity from the denominators. Then we are going to find the LCM of these two, 110 and 220, and definitely the LCM will be 220 times 10 raised to the power of negative 6. 220 times 10 raised to the power negative 6 divided by 110 times 10 raised to the power negative 6, that is 2. So 2 times what we have on the numerator, so that will be 2 into bracket 55,000 minus R2 times 1.2 minus 220 times 10 raised to the power negative 6 divided by 220 times 10 raised to the power negative 6, that is 1. So this is going to give us R2 minus, R2 times 2.4 being equal to 1.2 times 10 raised to the power negative 3 times 200 times 10 raised to the power 9 times the LCM the one that we had here, 220 times 10 raised to the power negative 6. So let's try to squeeze it here. 220 times 10 raised to the power of negative 6. So when you multiply these three, we are going to have 52,800. 52,800. Then we multiply 2 by 1.2, that is 2.4. Then open the brackets. 2.4 times 55,000. That happens to be 132,000 minus 2.4, that is 2 times 1.2, that is 2.4, times R2, that is 2.4 R2, minus, this one is going to be 2.4 R2 as well, is equals 52,800. Then you are going to take 132,000, the other side of the equal sign. Minus 2.4, that is minus 4.8. Minus 4.8, R2 being equal to 52,800 minus 132,000, that happens to be negative 79,200. To get the value of R2, we are going to divide both sides by negative 4.8. Divide this side as well by negative 4.8. And we are going to get R2 being equal to 16,500 newtons. So that is the value of R2. That is the reaction at the lower support. When you convert it to kilonewtons, going to divide by 1,000, that is going to be 16.5 kilonewtons. So that is the reaction at the lower support, or the total force in Mn. Now for us to get R1, we are going to use this relation, whereby R1 minus, that is R1 is equals 55 minus R2, and R2 is, in this case, is 16.5 kilonewtons. So when you do that, you are going to get a force of 38.5 kilonewtons. So we have the values of the reaction on the upper support and reaction on the lower support. So we have answered the first part of this question. The second part of the question, find also the stresses in the bars. So the stresses in the bars will be as follows. Now, we know that stress, let's start with stress in the upper bar, that is Rm. Stress is given by rod, and in this case the rod is R1 divided by cross-sectional area. So cross-sectional area of the bar Lm. In this case, R1 is 38.5 kilonewtons divided by cross-sectional area of Lm is 110 times 10 raised to the power of negative 6. That is going to give us a stress of 350,000 kilonewtons per square meter. So that is the stress in that particular bar. Then the stress in the lower bar, that is Mn. Stress in Mn will be given by force, which is the reaction R2 divided by cross-sectional area of the lower bar. So in this case, the force R2, that is 16.5 kilonewtons, cross-sectional area of the lower bar 220 square millimeters, convert to meters squared. So 220 times 10 raised to the power of negative 6. And that is going to give us a stress of 75,000 kilonewtons per square meter. So that's how we go about it. So we are through with that question, and thank you for your continued support. Subscribe if you are not yet a subscriber. Thank you very much. Let's meet in yet another lesson.